Okay, last time we talked about kinetics, which is how fast chemical reactions occur. And I told you if we had a chemical reaction, A plus B goes to products, how fast A and B get converted into products depends upon the concentration, the physical state. We're not going to focus on physical state too much. Concentration, physical state, temperature, and the presence of a catalyst. And here we're going to actually define reaction rate. Again, for a chemical reaction, A plus B goes to products, okay? And the way that we can measure the rate of a reaction is if A collides with B to make products, that means if A collides with B to make products, that means A is getting used up over time. So the concentration of A will go down over time. Similarly, it also means B is getting used up over time, so the concentration of B will go down over time. And if A and B are colliding to make the products, that means the amount of product, the concentration of product, will be increasing over time. You're making more of it. So what we're going to do here is take a hypothetical graph where I mix chemical A and chemical B to make P the product. And then over time, over a period of seconds, I measure the concentration of chemical A in my reaction container, and I measure its concentration over time. Maybe I have a special laser that measures the concentration, or I might do it through UV vis. There's different techniques for measuring the concentration. So, let's say we made this graph. I took 2 moles of A, 2 moles of B, put them in a 1 liter container. So the starting concentration of A is 2 moles per liter, or 2 molarity. We're going to measure how fast chemical A disappears over time. And these little dot circles, I don't know if you can tell, but I did them in purple, just like A is in purple. Those little dots are the actual data points that I collected. Then, based on the graphing rules that I taught you guys how to do, I did a best fit curve for these data points. Remember, if the data points look curvy, you're probably doing a best fit curve. If the data points look like they're making a straight line, you would do a best fit line. Here, the data points clearly look curvy, so I did a best fit curve. And I got the starting concentration was 2 molarity at 0 seconds. And it goes down and heads towards 0 molarity at 100 seconds. The rate of the reaction is defined as, here, let me write it. It's going to be equal to the change in the concentration of A over the change in time. Sloppily written, I apologize for that. Well, how are we going to measure the change in concentration over the change in time? Well, at 0 time, we would have our starting concentration of 2 molarity, and at 100 seconds, we would have an ending concentration that was a little bit above 0 molarity. The way we're going to get the change in concentration is we're going to get the delta of the concentration, where the delta is the final concentration minus the initial concentration. So here, the change in concentration will be the final concentration, whatever this is, minus the starting concentration, which is 2.0, divided by the final time, which is here in this example 100 seconds, minus the starting time, when this example was 0 seconds. You'll know, and I'll put some numbers in here and we'll calculate. But you'll notice I have a minus sign out in the front. How come I have a minus sign? When I measure the concentration of the reactant A disappearing or the reactant B disappearing, the concentration is going to go down. So my starting concentration will be a big number, in this case 2 molarity. My final concentration will be a small number. When I do a small number minus a big number, I'm going to get a negative number. This extra minus sign in front keeps the whole thing positive. Okay? That's why we have that extra minus sign. If we're measuring the rate of the reaction in terms of how fast A or B disappears. We'll do this later. If we're going to measure the rate of the reaction and how fast P appears, we would not have a minus sign. So again, the rate of this reaction is going to be the final concentration minus the starting concentration divided by the final time minus the starting time. Or written a little more easily, they'll say the rate of the reaction is minus delta concentration of A over delta time, where delta is always final minus initial. Remember, the initial is going to be here and the final is going to be out here. And again, I rewrote where delta A is final concentration minus initial concentration, and delta T means final time minus the initial time, final minus initial. So, if I want to calculate the rate of this reaction, from 0 seconds to 100 seconds, I would go the rate is equal to minus T final minus T initial is the easy part. What's the final time if I go from 0 to 100 seconds? The final time is 100 seconds. The initial time is 0 seconds. If I go from 0 to 100 seconds, what was the starting concentration on my graph? 2 molarity. What's my final concentration? I'm going to have to read it off the graph. It didn't quite reach 0. And given that this is 0, that's 1, and that's 2, that looks like that might be about 0.1 molarity. So if I want to calculate the rate of the reaction, I have, turn my calculator on, 0.1 minus 2 is going to give me negative 1.9. What are the units? Molarity divided by 100 minus 0, 100 seconds. See how I had 0.1 minus 2? That gave me that negative 1.9 or 1.9. Then this other minus sign out here makes it positive. Now when I do that, when I divide that by 100 seconds, I'm going to get the rate equals negative times the negative is positive, 0.019 molarity per second. That's the rate of this reaction if I measure it from 0 to 100 seconds. Okay? And again, this is rate equals minus delta A over delta T. Suppose I didn't want to know the rate over 0 to 100 seconds. Maybe I wanted to know how fast it was going from 0 to 50 seconds. I'm going to get a different number when I do that. Let's go ahead and do from 0 to 50 seconds. So this is 0 to 100 seconds. Let me recalculate between 0 to 50 seconds. That's going to be minus final time. Oh, what did I say? 0 to 50 seconds is what I want to measure now. The final time is 50 seconds. Remember, T final is 50 seconds. The starting time is 0 seconds. What was the starting concentration? 2 molarity. If I'm looking at 0 seconds, then it's 2 molarity. What is at 50 seconds? That looks like, we could all estimate it differently. Looks like maybe 0.4 or 0.5. I'll go with 0.4 molarity. 0.4 minus 2 is going to give me a negative number, but this other negative sign over here is going to give me a positive number. So that's going to give me 0.4 minus 2. Give me that. And that's going to be so the rate will be 0.032 molarity per second for 0 to 50 seconds. This means several things. First off, how come these numbers are different? Well, at high concentration in the beginning, remember what I told you? High concentration means lots of collisions, so therefore a very fast reaction rate. As chemical A gets used up and its concentration goes down, the rate of the reaction slows down. So up here, with high concentration of A colliding into B, it's going really fast, steep slope down. Over here, there's not much A left in the reaction anymore, so it takes a long time for those collisions to happen, so the rate of reaction will be slower. Okay? So if I measure it between 2 different time intervals, here from 0 to 100 seconds includes the fast piece, the medium piece, and the slow piece. If I measure the rate of the reaction between 0 and 50 seconds, it would include this fast time and this medium time, but not the really slow time. So between 0 and 100 seconds, it'll be a smaller number or a slower average reaction rate than it would be if I took the average reaction rate between 0 and 50 seconds. When I say average reaction rate, that means I only looked at the concentration here and the concentration here, and I didn't look at every little concentration along the way. I just averaged it. Okay? So, I got 2 different numbers because the average from 0 to 100 seconds includes this slow reaction rate where there is low concentration of A and very few collisions, therefore very, very slow reaction. Here, this is like the first 50 seconds, it's going to be a faster average because I have higher concentration here. So higher concentration of chemical A means more collisions, therefore a higher reaction rate. This gives me an actual number. This tells me the concentration of A between the first 50 seconds is an average, or the average reaction rate is 0.032 molarity per second. And over here, the average reaction rate over the whole interval is 0.019 molarity per second. Okay? So, what we did here was do a basic definition of reaction rate. Remember, reaction rate is affected by concentration, physical characteristics, temperature, and catalyst. At 0 time, we have a high concentration of chemical A. That's the highest in our experiment. That means we're going to have a really fast reaction rate, and the concentration line goes down steeply. Out here, my concentration of A is much lower because it's gotten used up. So therefore, for the reaction to keep going, I have to wait till the few last chemical A bump into B to make products. It's going to be a slower reaction rate. The reaction rate is defined as the change in concentration of A over the change in time, or, where did I have it? Right here, minus delta A over delta time, where minus delta A means A final minus A initial. Remember, this is A initial, A final's down here. T final minus T initial, this is T initial, T final's over here. Notice I have a minus sign here, an extra one. Why is that? That's because final is going to be a smaller number than initial. So when I subtract these two, I'm going to get a negative 1.6 molarity. This extra minus sign makes sure that I have a positive sign when I'm done for the rate of the reaction. These are both here average reaction rates. In one experiment, I wanted to know the average reaction rate over a period of 100 seconds. Next experiment, I wanted to know the average reaction rate over the first 50 seconds. That might be analogous to, let's say I have a marathon. Somebody's running a marathon, and I want to know the average speed over the 24 miles, something like that, of a marathon over the whole 24 miles. Well, in the beginning, people are going to be running faster, and towards the end, people are going to be running slower. So my average is going to be a smaller number than if I measure it in the first 10 miles of a marathon. I'm going to have a higher average speed because people aren't gassing out yet. Marathon runners aren't gassing out yet. So I'm going to have two different numbers, and this gives me the average reaction rate. I could also define the average reaction rate here. In my pretend experiment, I measured the concentration of A disappearing over time. What if I measured the concentration of B disappearing over time? Well, the rate of the reaction would be minus delta B over delta T, or minus B final minus B initial over T final minus T initial. I got this extra minus sign because B is a reactant and it's disappearing, so this will be a small number, that'll be a big number. Small number minus a big number gives me a negative number, and then another negative makes it positive. If I defined the reaction rate in terms of P, the product, disappearing, I would have delta P, oh, that's sloppy, delta P over delta T is equal to P final minus P initial over T final minus T initial. How come no minus sign here? That's because when I'm running the reaction, P is going to go from low concentration to high concentration. So this will be a big number minus a little number. That'll give me a positive, so I don't need the extra minus sign to make it positive. So here, and again, right now, today, we're talking average reaction rates. I would define the reaction rate as equal to, in this case, if I am talking A plus B goes to P, I would say minus delta A over delta T is equal to minus delta B over delta T. It's equal to, I'm going to put it here, a positive delta P over delta T. This is average reaction rates. The next time we're going to do instantaneous reaction rate, and initial reaction rates, but I wanted to get this up for now. Okay? All right, and we'll end there.